morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make general chemistry part of your day. I'm going to try to hammer out two quick calculations using partial pressures and the ideal gas law, and showing how you can look at the total pressure and how that can affect the calculation in two different ways. One to make it easier and one to make it harder. So let's start with the hard and then we'll go into the easy-ish. And let's take what is a common type of problem where you collect a gas over water, bubble it through water, out of aqueous solution becomes a gas. So the phrase you want to look for in these word problems is going to be this idea of collected over water. Specifically, let's look at this problem. We're going to get nitrogen gas by breaking down ammonium nitrite, and we'll get water and nitrogen gas. This will bubble through the liquid water. And what happens here is a little bit of a trick. But let's go and read the word problem. We collect over water, 25 Celsius, 727 torr, how many liters? 5.68 grams of ammonium nitrate. So again, everything that's there, underline it, give me a letter. V, T, P, and N. This is clearly one version, P equals nRT. We're going to plug and chug into that. So there's the trick here is the collected over water. Because when we get this pressure is our total pressure, the 727 millimeters of mercury. And we want to do nitrogen and nitrogen here, going back to the idea of partial versus total pressures. So how do I do that? Well, I'm going to have to subtract out the water, because what we have to realize is when we collect over water, we get water vapor in there as well as whatever new gas we're making. So where do we get the pressure of water? This is going to be one of those ask Bob, back of the book, find an appendix, find a table in the chapter and look it up. I've taken a little truncated piece of a table here where we have pressure of water over various temperatures. So this is 25 degrees Celsius, so I'm going to use this line, and the partial pressure of water is 3.8 millimeters of mercury. We want to know what the pressure of nitrogen is, and we know our total is 727. So if we solve for the pressure of nitrogen, we get 703 millimeters of mercury, divide by 760 millimeters of mercury, and we get our atmospheres. And if it makes any of you feel better, I just did this calculation wrong, and I'm redoing it now to get it right for you guys on the video. 25 ATM. We're solving for V. Our moles of nitrogen we're going to get from this. So it's going to be 5.68 grams of ammonium nitrite. And that is 64.06 grams per mole. And we really need to do a mole-to-mole ratio because we need nitrogen. Now, for once in my life, I gave you an easy one where the mole-to-mole ratio is 1:1. But nevertheless, we should do that. We should do our math right. 0.887, I believe. Oops. 0.0887 moles. Alright, I'm sorry about my board spacing. This is terrible. R is 0.0821, and my temperature is 298. If I solve for my volume, I get a volume of 2.35 liters of nitrogen gas to be collected. So the only trick here is with this phrase of collected over water. If that's the case, you have to realize that your total pressure, which is what will be given to you in the problem, is going to be the pressure of the gas you care about, plus the pressure of water. So you can subtract out the pressure of water. You get that from a table in the back of the book. Otherwise, it looks a lot like a normal PV equals nRT. As always, look at your labels. Make sure the grams you have here is actually a gas, which I left out. Is a gas, and that we're talking about the same chemical. If not, remember, do your mole-to-mole ratio. So, another version of this, working on these same ideas, mixtures, stoichiometry. So gunpowder can be composed where it's 75% potassium nitrate by mass. If 1 gram of gunpowder is ignited, what volume will the gases occupy at 720 torr and 25 degrees Celsius? So again, pressure, temperature, volume, amount. This is a single PV equals nRT. And I think pressure is pretty straightforward. 720 over 760. my volume I'm solving for. Moles I'm going to come back to. R is R and T is in Kelvin. So the only tricky part here is how do I get the moles? Because we have 1 gram of powder, that's not even a chemical. Oh, and I totally forgot a piece of the problem. Let me put a very important piece of the problem down. 4 potassium nitrates plus 7 carbons plus a sulfur gives me K2CO3 plus K2S plus 3 carbon monoxide gas molecules plus 3 carbon dioxide gas molecules plus 2 nitrogen gas molecules. These are all solids. Solid, 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 solid. Okay. Sorry about that. Forgot a very important piece of the problem. Okay, so there's nothing powder here but 75%, so we can say it's 75 KNO3 over every 100 powder. If you want to do it that way, you could just multiply by 0.75 and realize 1 gram would be 0.75. But mathematically, that's what we're looking at here. So now we got grams of KNO3. We want to convert that to moles. And then we can use the mole-to-mole ratio. Because again, this is a solid, so it's not helping us get gases. But the trick here is, we don't need, we can, again, the ideal gas law tells us we can combine all these together. So we have 3, 3, and 2, or 8 moles of gas in total. And that's all we need here. So this number then we can drop right down here. 0.0148 moles. I can calculate for my volume. And I get 0.383 liters. So again, same setup we had before. Stoichiometry, P equals nRT, make sure our units are right. Kelvin, atmospheres, moles. But the trick here is this actually makes it simpler. We can, instead of doing 3 calculations and adding the partial pressures together, we can realize that that ratio is conserved and we're getting 8 gas particles for every 1 KNO3 that decomposes. We're done with Dalton's law. We're essentially done with the math in this chapter. I do want to talk about concepts, what's behind the scenes. We've been talking about that already. And what was the other fantabulous thing I was supposed to talk about? Oh, speed of gases and speed of gases through a hole. And not to give it away, but lighter things move faster, and everything's related to collisions, which I've already been trying to sprinkle in as we go through the videos. But I'll formalize that, and then we're done with gas laws. We're ready for test number 3, and I hope you feel good about that. Have a wonderful, wonderful day.